This is Mr. Liao, and we're on Chapter 10 for AP Stats, Estimating with Confidence. Today we're going to learn how to explain statistical inference and how probability is used to draw conclusions. We're going to look at the basic form for all confidence intervals, explain what is meant by the margin of error, and state what is meant by a level C confidence interval. So let's suppose we wanted to figure out the percentage of the population that approve of President Trump's job performance, or learn the mean weight of all high school senior boys. It's impossible to ask everyone in the population these questions, so we're going to have to make estimates based on samples. So as we learned in the last chapter, statistical inference provides methods for drawing conclusions about a population from sample data. Most of the time you only get one sample. Now, sample values, or statistics, will vary depending on the sample. That's the idea of sampling variability. Every time you take a sample from a population, you're going to get a different composition of subjects, so your numbers will be a little different. However, the population values, or the parameters, will not change. They are fixed, but they are often unknown. So let's use this example. Let's suppose we want to know the mean SAT math score of all 350,000 California high school seniors. So you don't know the true population mean. You give a test a sample of 500 students and you end up with a sample mean of 461. So based on this, what can you say about the mean score mu in the population of all 350,000 seniors? Well, we learned from the last chapter that if you take many samples of 500 from the same population, that would be a sampling distribution. CLT allows us to approximate normality for the distribution of X bars. That's because the sample size of 500 is well above 30. We also know that the mean of this distribution is mu, and the standard deviation is sigma over the square root of 500, and we can use that because of the 10% condition. Okay? So let's now suppose that the standard deviation is 100. So our standard deviation for this distribution is 100 over the square root of 500, so about 4.5 points. Now this is how we're going to do statistical estimation. First, to estimate the unknown population mean mu, we're going to use the sample mean of our SRS. So you take one sample, and that sample mean is going to be the basis of our estimation for the population mean mu. 2, although X bar is an unbiased estimator of mu, in other words, if you repeatedly take samples of the population of the same size and take the mean of all the X bars, you will get mu. One single X bar will rarely be exactly equal to mu due to sampling variability, so our estimate will likely have some error. It's not going to be exactly equal to the population mean mu. Now, in repeated samples, the value of X bar will approximately follow a normal distribution due to CLT, with the mean mu and a standard deviation of 4.5. So even though we don't know the population mean, if we know the population standard deviation is 100, for a sample size of 500, that standard deviation is going to be only 4.5 points. Now, since that distribution is normally distributed with a mean of mu and a standard deviation of 4.5, the 68, 95, 99.7 rule says that in about 95% of all samples, the mean score X bar will be within 9 points of the population mean mu. Okay, now if you think about it this way, remember the mean population mu is the center of the distribution. 9 points is 2 standard deviations, and 95% of all values are within 2 standard deviations. So X bar from any single sample will be within 2 standard deviations of the mean 95% of the time. In 95% of samples will the X bar be within 2 standard deviations of the mean. Now, whenever X bar is within 9 points of the unknown mu, that means, conversely, the mu is also within 9 points of X bar. That's like saying, if I'm 9 miles away from you, you're 9 miles away from me. And this is also going to happen 95% of the time. So in 95% of samples, the unknown population mean mu is going to be between X bar minus 9 and X bar plus 9. So X bar plus or minus 2 standard deviations. So somewhere between 452 and 470. So here's an illustration of what we're looking at. We have the population mean mu in the middle, and we have values of X bar. We have 1 standard deviation from that, and the sampling distribution of X bar. Now, if you take all the values within 2 standard deviations of the mean, mu, you will see this 95% region. Now, in that region are all the X bars between mu minus 9 and mu plus 9. 95% of all X bars are in that interval. Now, that also means the X bar has a 95% chance of being within 9 points or 2 standard deviations of the population mean mu. So there are two possibilities. The interval between 452 and 470 contains the true population mean mu, or we got one of the samples that was not within 5% of the population mean mu. In other words, it was at least 2 standard deviations of the mean. And again, that's going to happen about 5% of the time in a normal distribution. So ultimately, we can only say we're 95% confident that the unknown parameter mu lies between 452 and 470. Again, 452, 470 is within 2 standard deviations of our x bar. And remember, if mu, 90% of all x bars is within 2 standard deviations of mu, then likewise mu is going to be within 95% of all x bars. So we call this interval of numbers between the values of x bar plus or minus 2 sigma a 95% confidence interval for mu. So we're going to use this form for a confidence interval, a point estimate or statistic plus or minus the margin of error. In this case, the point estimate was x bar. Now remember, x bar is a sample mean, and a sample mean is a statistic. So a level C confidence interval parameter has 2 parts. First, it has an interval calculated from the data, usually of the form point estimate plus or minus margin of error, or statistic plus or minus critical value times the standard deviation of the statistic. So the thing to the right of the plus minus sign is equal to the margin of error. The critical value depends on the test and the confidence interval, and the standard deviation statistics is based on the standard deviation. Also, a confidence level C, which gives the overall success rate that the interval will capture the true parameter value in repeated samples. So this is an illustration that will help kind of see what's going on. Here we have x bar ranging left to right, and mu is in the middle. Now what you see below are all these lines that are 2 standard deviations wide. So if you notice, there are 25 lines, all 2 standard deviations wide. They have a dot in the middle. Those represent different x bars, different sample means. Now notice, different sample means are going to vary. Some are going to be below the population mean mu, some are going to be above. Now if you notice, all the values, all the widths being 2 standard deviations wide, most of them capture the population mean mu. So the left-right distance of x bar represents where it is on the x-axis. The width of the interval will often capture the population mean mu. That's represented by the vertical line. Now you will notice in one of those intervals, it doesn't capture the population mean mu. This is one of the sample means that was more than 2 standard deviations from the mean. This would happen about 5% of all samples. So just by chance, 5% of the time, you are going to get a sample mean 2 standard deviations away from the mean or more, which means if you take a width of 2 standard deviations to each side, you are going to miss the population mean mu. So here's a simulation on a website, and this is going to be basically doing the same thing. So I'm going to set the population mean to mu. The sigma is 10, the sample size is 50, it doesn't matter. So what you're going to see as I sample this, you're going to see a vertical line that represents the population mu 0. You will see a bunch of black dots. Those represent different x bars from different samples from the population. And each of those green lines or red lines represents the width. 2 standard deviations to the left, 2 standard deviations to the right of x bar. Now you'll notice all the green lines capture the population mean mu. It captures the vertical line. However, there are 6 red lines where the x bar is too far away from the population mean mu to capture the population mean. So think of the confidence interval as like a net when you go fishing. You're going to drop the net based on your calculations where you think the fish will bite. If the fish bite where you think they'll bite, 95% of the time you will capture the fish in your net. But 5% of the time you won't, and that's because you set the net too far away from the fish to capture it. That's what the red lines represent. They are too far away from the line to capture it. They're more than 2 standard deviations away. The net is not wide enough. And we can keep doing this. You see, this one out of 100 captured the population mean 94% of the time. Now if we do another one, you will see this one captures it 95% of the time. This one captures it 93%. And if I can keep going, you can see a running total. If I keep going, it'll eventually approach 95%. So in a very large number of samples, 95% of the confidence intervals would contain the population mean mu. This is the applet that I just showed, so if you want to play with it on your own, you may do that. Now, to interpret confidence levels, we say we are 95% confident, which means 95% of all possible samples of a given size from this population will result in an interval that captures the unknown population parameter. To interpret a confidence interval from an unknown parameter, we're going to say this, and this is something you're going to write so many times that you will know this like the back of your hand. We are C% confident, whether it's 90%, 95%, 99%, we are C% confident that the interval from point A to point B captures the actual value of whatever the population parameter in context. So we're 95% confident that the interval from 452 to 470 captures the true population mean mu of all average SAT scores for California SAT test takers. Now, a confidence interval is not a probability. The unknown parameter is a fixed value. We just don't know exactly what it is. So the value is actually going to either be in our interval or it's not. It's not 50% or 95%. It's either 0 or 1. So what's the probability that mu is between 452 and 470? It is not 95%. After you construct the confidence interval, there are only two possible outcomes. Either the population parameter is captured, which means the probability is 1, or it's not, which means the probability is 0. So the analogy I would give is this. If I flip a coin, before I flip it, if I ask you, hey, what's the probability that this comes up heads, you would say 50%. Now, after I flip the coin and before I show it to you, what's the probability it's heads? Well, the answer is either 0 or 1. The event has happened. The outcome is there. You just don't know what it is yet. That's the idea of how a confidence interval works. It's like the coin is flipped. You just don't know what it says. And you're trying to make your best estimate as to what it says. So an example based on hot dog fat, who doesn't love hot dogs, how much fat is in brand X hot dogs? To find out, researchers measure the fat content in grams of a random sample of 10 brand X hot dogs. A 95% confidence interval for the population mean is between 2.84 and 7.55 grams. So first we're going to interpret the confidence interval. So the confidence interval means we are 95% confident that the interval from 2.84 to 7.55 grams of fat captures the true mean fat content of brand X hot dogs. So here is the format that you're going to use. We're 95% confident, that states the confidence level, that the interval from, in this case, 2.84 to 7.55, whatever your interval is with the units, captures the true parameter value of the population characteristic you're trying to measure. In this case, the true mean fat content of brand X hot dogs. So remember this format. Remember this style. Next, we're going to interpret the confidence level itself. This is a little different. In 95% of all possible samples of 10 brand X hot dogs, the resulting confidence interval would capture the true mean fat content. Okay? So 95% of all possible samples of size 10, you will get an interval that captures the population mean mu, which means 5% of the time you won't. Number 3, the interval from 2.84 to 7.55 has a 95% chance of containing the actual population standard deviation mu, and this is false because, again, the probability is either 1 or it is 0. That's it for section 10.1, estimating with confidence. If you have any questions, feel free to ask me when we come back to class.